All right, so we're going to do some problems here with this understanding of the calorimeter is going to be part of this equation. Again, I'm just going to show you where it fits in to what we've been talking about so far. So I have a 60-gram sample of water at 84.3 degrees Celsius is added to 50-gram water at 23.2 and a coffee cup calorimeter. Calculate the calorimeter constant if the final temperature of the mixture is 55.7. Okay. So I'm going to have the hot water over here on the left, and that side's going to be the negative because it's losing the heat. And then I have the cold water, and then for this, we're going to have the calorimeter, or essentially the coffee cup on this side. Okay, because again, that's where the cold water is. It makes the most sense to have it on that side. So what information do I have about the hot water? So I have 60 grams of it. I have a specific heat of 4.184 joules per gram degree Celsius. And then I have the final temperature is 55.7. And my initial temperature of the hot water is 84.3. So that's going to be over here on the left, and that's going to all be negative due to the fact that that subtraction there is going to end up being a negative number. So then the cold water, I have 50 grams, 4.184 joules per gram degrees Celsius. And then this change in temperature is going to be 55.7 as the final temperature, but the initial temperature of that water, what I call the cold water, is 23.2 degrees Celsius. On this side, I also have the calorimeter. Well, I don't know the calorimeter constant, that's what I'm trying to find, but I know that the calorimeter itself has the cold water. So that's going to be the temperature change is going to be the colder water because you're dumping in the hot water into the cold water. So pause the video and see if you can calculate essentially what the calorimeter constant is, what the calorimeter constant is. So you should have gotten 11.7 joules per degree Celsius. Again, calorimeter constant's always going to be in this unit. So it is, I'm not really going to use this calculation too much, but I am going to show it to you in one more way to kind of use it as a tool. So this problem here is using the same calorimeter, so that has the actual answer of the previous problem. The temperature of 50 grams of water at 25 degrees Celsius contained in the same calorimeter decreases. Okay, so we're going to see that the temperature decreases to 24.39 when 1 gram of potassium chloride is added and the mixture is stirred until all of the solid dissolves. Calculate Q if the specific heat of the resulting solution is 4.18 joules per gram degrees Celsius. So this is what we call a heat of solution problem. And this is a little more tricky in terms of what's taking place and who's the system, who's the surroundings. So I do like to spend some time on this one because it is a little bit more confusing when you first look at it. So I'm going to draw a beaker over here of what's really happening and what we want to look at. So potassium chloride is KClO3. That's the formula of potassium chloride. And I'm throwing that into a beaker of water, okay? And I'm going to put a thermometer in here to kind of watch the temperature change, okay? So when I am doing what we call heat of solution type problems, what I typically do is write the solid on the left. I write an arrow. I put water above the arrow. You sometimes see this in other resources as well. And then it's breaking up into its ions, okay, aqueous ions. And it says all of the solid dissolved. So when we're looking at this chemical reaction here, okay, the water really is part of this, the discussion, but it really is going to be what we call the surroundings. Because really the breaking up of these two ions is the chemical reaction. That's the system, okay? So the water is going to be considered the surroundings. So when I put the thermometer into the water, I'm measuring the surroundings, not the system. So that's where the signs on this one is going to get kind of crazy, okay? So the Q of the reaction, okay, this is the chemical reaction we're talking about, is due to the water and the calorimeter. Okay, so I am going to look at what information do I have about the water. Well, I have 50 grams of the water. I know the specific heat of water is 4.18 of the whole solution. And again, just putting 1 gram of that potassium chloride really is not going to change the specific heat of that overall. So what's my change in temperature here? Well, it decreases to 24.39. So that's my final temperature, and my initial temperature is 25 degrees Celsius. So to that, I'm going to have the calorimeter constant of 11.7 joules per degree Celsius, and my change in temperature is exactly the same. All right, so recognize my delta T here is negative, okay? I end up with a negative value here and a negative value there, okay? So if I do the math, it comes out to be 127.6 joules here, and then this comes out to be 7.1 joules, okay? But they are added together, okay? They're both negative, so they become negative 135 joules, okay? If I use the delta T. But think of this logically, okay? If I'm dumping the potassium chloride into water and the temperature is going down, okay, the temperature is going down, that means the water itself is losing the energy. And the energy is going into breaking up this solid, okay? So is the Q of this reaction really going to be negative? No, okay? This is actually an endothermic process, all right? So what's tricky about heat of solution is the delta T is not going to help you. It's actually going to confuse you further. What you have to consider when you're dumping a solid into water is you're measuring the water, okay? You're measuring the surroundings. So keeping that in mind, you have to then look at the sign and say, is that a correct sign or not? Or just don't look at the delta T and then determine the sign at the end. Okay, so if this was an exothermic process, that means if this was dissolving, it would release energy. You would see the energy flow into the water. Well, then the water's temperature would go up, okay? But your delta T here would end up being a positive value, okay? So for heat of solution problems, you are going to have to really examine. You can't just use the math to help you out. All right, so this is Q, okay? Well, what if I dumped in 5 grams of potassium chloride? Okay, what if I did 5 grams instead of 1 gram? Well, what would happen to my delta T? Okay, so my delta T would change, all right? My delta T would change. So then my overall Q would change, all right? So Q is dependent upon how much stuff you put in there, all right? We have another unit that we're going to talk about called delta H, okay? And its unit is kilojoule per mole, okay? Now this is just joule. You could change it to kilojoule as well, but it depends upon how much I put in there, okay? So if I convert 1 gram of potassium chlorate to moles, okay, so if I add up potassium and chlorine and 3 oxygens, I get about 122.5 grams. So it's about 0.0082 moles is how much potassium chloride I put in this experiment. So what's my delta T going to be? Well, I'm going to convert the joules to kilojoules because that's the unit of delta H. So that's going to be 0.135 kilojoules. And then how many moles do I have? 0.0082 moles. Okay. So I end up with a value of about 16.5 kilojoules per mole. So if I did the experiment with 5 grams, okay, so I would have more moles on the bottom, but then the Q would also be larger as well. So the thing about delta H, okay, it's a positive, this is an endothermic process. Delta H doesn't change. This is a constant for potassium chloride. So this will always remain the same. The Q is going to change because that's going to depend upon how much stuff you have. All right. So delta H is going to be what we talk about next. It's called enthalpy. Okay. And this is going to be a constant for the reaction. So this is a long time ago. If your delta H was positive or negative, determined if you were exothermic or endothermic process. Okay.